Hi, I'm Zor. Welcome to Unizor Education. Well, we continue talking about functionals because they do play a very important role in physics. But we are approaching, I would say, more mathematically right now, just to prepare you for whatever the usage we will have in physics. Now, this lecture is a continuation basically of whatever I have started in the previous lecture, where we introduced the two very important concepts: the concept of functional and the concept of calculus of variations, which is basically a tool for functionals equivalent to calculus for functions. Calculus for functions primarily appeared from the need to basically find out the behavior of the function, its maximum, minimum, increasing, decreasing, etc. For functionals, calculus of variations plays exactly the same role. And we will concentrate on maximum and minimum of functionals and how to basically approach the problem of finding these maximum and minimum. This lecture is basically called Max-Min of Functionals, where I will just try to define what is a maximum or minimum of functional. Okay, now you do remember what functional is. Again, we introduced it in the previous lecture, but in two words, this is basically a function of function, so to speak. We're all familiar with functions of one argument, let's say one real argument, functions like this one. So one argument, real, for example, and the value is real number. We also can consider function of n different arguments, where you will put n real numbers and get as a result some real number which is the function of these real numbers. And the functional is a function of function. Let's talk about one function. Is an argument to a functional. Example, well, if you have a function, then you can, for example, consider integral of this function on some segment from a to b. Well, this is a real number, and it depends on an entire function, on its behavior. So that's what basically it means, functional. Okay. Now we have to approach the problem of how to define minimum and maximum. And well, obviously, all of you know what minimum and maximum of function is, and at least for me, it's always associated with geometry. I mean, geometrical kind of interpretation of function. If the function is given as a graph, then there is a concept of local minimum, which is this one. It means that somewhere near this particular value of argument, no matter where we go, to the left or to the right, we will always increase the value of the function. So that's the minimum. And we will primarily talk about minimum because maximum is absolutely the same. You just have to change less or less than sign to greater or greater than. So we'll talk about minimum. Now, is it absolute minimum? No. For instance, in this case, function's value is less than this. So we're talking only about local minimum. Local means that in a very small neighborhood of this particular point, which we suspect to be a local minimum, the function will only be greater in its values. So this is a kind of geometrical view. Now, let's talk about functions of many arguments. Let's say 2. If you have a function of 2 arguments, well, we can imagine that this is something like this. So this is my three-dimensional x, y, z. And this is kind of a paraboloid, if you wish. Well, this is a local minimum. Now, but what does it mean that this is a local minimum, mathematically speaking? Well, we can define it in a very simple way. If we will go to a very small neighborhood of this point, and we will talk about what is a small neighborhood, then from any point, if you will take the value of the function, it will be greater than the value in the center of this small neighborhood. Okay, now everything is great except small neighborhood. What is a small neighborhood? Well, in n-dimensional Cartesian space, there is a concept of distance, right? If you have a function, if you have two different points, let's say in this case point, let's say x0, y0, and we will take any other point not very far from it, there is a concept of a distance between them. Distance, let's put it this way. What is the distance? Well, the distance is defined as square root of x1 minus x0 square plus y0 minus y0 square. Right? Right. Now, I would like actually to do it a little bit in a simpler formula, because what is xy minus x1 minus x0, 1 minus y0? Well, if you take this point and have a vector from point x0, y0 to point x1, y1, the coordinates of this vector would be x1 minus x0, y1 minus y0. That would be a vector. So if this is vector p, and this is point q, this is pq. Correct? And this is the length, this is the length of the vector pq. So we have defined basically the neighborhood as number of points with the vector from the minimum point to this any point for a small neighborhood. So the length of this vector should be less than something. Now, mathematically speaking, it's something like this. What is a local minimum? Local minimum is that there exists, I will use this symbol, exists some kind of a small number epsilon greater than 0, such that if pq length of this vector less than epsilon, then value of our function at point P would be less than or equal to value of our function at point Q. So this is basically a definition of a local minimum. There exists an epsilon, so small epsilon neighborhood or radius, if you wish. It's n-dimensional radius because there are n coordinates. In this case, it's 2. Such that the distance from a center to any point within this n-dimensional sphere, actually. So for any point within this distance, point in the center of the sphere is less or equal to value of the function in that other point. Okay, fine. How to find this point? Well, we know that for a function of one argument, what we do? Well, we do first derivative and equate it to 0. Why? Well, first derivative is a tangent of a slope of tangential line, right? tangential line. Now, since this is function is decreasing here and increasing there, that's what minimum is. It's decreasing on the left and increasing on the right, right? So which means it's decreasing, which means the angle would be of the tangential line would be greater than 90 degrees, and when it's increasing, the tangential line would be less than 90 degrees. And tangent of less than 90 degrees would be positive, and if it's greater than 90 degrees, it would be negative. Well, if it changed the sign from negative to positive, somewhere it should be equal to 0, right? If something is changing from negative to positive, it crosses 0, and 0 is exactly the point where we have the horizontal line, and horizontal line, tangential line, is actually minimum. Obviously, it's all for nicely differentiable functions without any kind of jumps or whatever else. For nice functions, we'll call them nice functions. Okay, for nice functions, that's how we decide this. What to do in this particular case? Well, when you have many dimensions, here is an alternative way, which we can actually reduce the problem of finding a minimum within n-dimensional sphere, because we don't know which direction to move. In this case, it's left and right. And in between left and right, between decreasing and increasing, there is always the 0 point. In multidimensional case, we don't have this direction, so to speak. But we can actually do it this way. Let's choose any unit vector. Doesn't really matter which one. Call it E. Now, what if you will do the following things? Vector OP, which is this, plus some kind of a multiplier, real number, this vector. Well, if this vector is this, you will have, and where t would be in some range from 0 to some kind of a tau. So if you will have this one, then you will have points from p towards this direction, from let's say OP plus 0, which is OP, which is that center, to OP plus tau. The tau is the maximum multiplier. So it will be something like this. If you will change direction from E to this one, you will get this point, and this point, etc. So you will have, if you will change t from 0 to tau, you will have some kind of a neighborhood if you will have all these points of this type, right? So what if we will fix one particular vector? Well, you will have a direction, and you can always consider the function of OP plus TE. If E is fixed, it's function of only of real number t. It means all the points on this direction, from minus tau to plus tau. Well, actually it's only from 0 to tau, because we consider greater than 0. Okay, so you will have only this particular direction. And in this particular direction, you can always differentiate it by t and find what exactly is the first derivative by t. That will be a minimum within these particular pieces. Okay? And you will have something like point this, where the derivative is equal to 0. If you will change this unit vector, you will have a different direction. You will have something like this. So you can always consider a plane which is cutting our paraboloid in this particular case correspondingly to a direction of our vector E, unit vector E. So you can differentiate it, as I said, and you will get what is a minimum point in this section of the paraboloid, or whatever the graph of our function is. It's called a directional derivative. So using a concept of directional derivative like this, you can find the minimum point on some cutting of subsection actually of our function curve, function surface actually is n-dimensional, and this would be a function of one argument. So you can always consider the regular derivative as equal to 0 at point of minimum. And now we can say that the point of minimum of this multidimensional function is such a point that for any direction of this unit vector E, we will get the minimum of this particular at this particular point. Now, how can it be expressed mathematically like this one? Well, very simply. This point P should be considered as a minimum of multidimensional if for any directional vector E, we will have, there exists some kind of a tau, which is a small neighborhood, such that f of OP less than or equal f then vector OP plus t times E for any t which for any t in this range. So if this is really a point of minimum, then we can actually find some kind of a maximum deviation of this point in some direction, but it should be for all directions. That's why I have it for all E, for all unit vectors E. If this particular value in this function is less than all the values along a radius, so to speak, from a point of minimum up to the border of this multidimensional sphere. If we are still increasing in this direction, and in this, and in this, and in this, and in that, in all directions we increase, and that's the minimum. This is an equivalent definition of this one when I was talking about distance in Cartesian coordinates between points P and Q. However, what's the advantage? I cannot really apply regular calculus to this one, but I can if I'm doing something like this. Now, you can say that, well, that's for all the all the vectors E in all directions, so I have to check it for infinite number of directional vectors, right? But that's not exactly true, because in n-dimensional space, it's sufficient actually to choose only n different dimensions along the coordinate axis. And we will prove it in some time that basically if this is true, not for all the different directions, but only on n different directions along n different axes of coordinates, that would be sufficient because everything else can be expressed in that term. So basically it means that to solve this problem of finding minimum of a function, you really have to solve this equation n times for n different directions along n different axes of coordinates, which were called, if you remember, partial derivatives. So if partial derivative of function f of n arguments against every argument is equal to 0 in some particular point, so it's a system of n equations with n unknowns. So you have partial derivative one argument, the second argument, the third argument, etc. All partial derivatives should be equal to 0. Then you can suspect that this is minimum, or maximum, or some kind of a saddle point, but anyway, but it's a critical point. It's a stationary point, as mathematicians call it. So it's very important. This directional minimum and directional derivative are very important concepts. Now, I started from n-dimensional case because now it's easier for me to go into functionals which have infinite number of arguments, because function is infinite number of arguments. It's like a trajectory is a function. It's many, many, many points, infinite points. Now, in this case, we have n different real numbers. Function is infinite number of numbers, so it's more complex situation than this one. But using this approach, we can actually reduce the complexity of the function to basically a derivative by one argument, granted from many different directions, so to speak. Okay, so let's go to functionals. Okay. So we consider functional to be defined as a function of functions. So it's supposed to be defined, its arguments are certain functions. But we would like to concentrate only on nice functions. Nice functions are all defined, let's say, in some segment, and differentiable, well, at least double differential, so the second derivative exists. So they are smooth, nice. Now, okay, that's one. Secondly, I would like actually these functions to comprise a nice set of functions, which means if you have a function as one of the arguments to a functional, I would like this function multiplied by a number to also be part of the domain of this functional. So if you have a functional f of x, then f of x should be nice. As I said, it belongs to this, it's defined on this segment, including borders, including a and b. So we don't have any kind of a infinite growth or whatever. It's a function which can be actually defined like a graph from point to point. Okay, so if you multiply by some kind of a coefficient, I would like this also, and this is a real number, I would like that also be one of the functions for which a functional is defined. So it's one of the domain. Or maybe if you have a linear combination of two functions, this is also should be part of the domain of the functional. So functional is defined on a lot of different functions, but they are at least should be nice, and multiplied by real number should also belong, and linear combination as well. So, okay, fine, and that's not all, because if you remember, to define local minimum, we have to define it as a point, but make sure that around this point the value of functional would be greater. Now, what is around? What is a small neighborhood of function f0? Well, in the first definition, the similar to a distance in the n-dimensional case, distance from a point of minimum to any other distance in a small neighborhood. There is a concept of a distance. In n-dimensional case, we have Cartesian coordinates. In this particular case, we need something to define this small neighborhood. So we need a distance between two different functions? Well, here is my suggestion. Let's define, as we have in in vectors in Cartesian system of coordinates, we have a concept of a distance and we have a concept of scalar product. Remember, in case you have two vectors, x1, xn, and y1, yn, we have a scalar product which is, this is vector x, this is vector y, and their scalar product, x times y, that's x1 times y1, plus etc. plus xn times yn. So scalar product is defined, and the magnitude of a vector would be magnitude of the vector x would be square root of its product to itself. If its product to itself would be x1 square, etc. plus xn square, if I will multiply x by x. So it would be sum of the squares, so square root would be the length of the vector. So we have, from scalar product, we have also the magnitude of the vector. So whenever we are saying about small neighborhood in the dimensional space, we can always say, okay, this is defined as magnitude of the vector from P to Q. Magnitude of this vector. Now here we also need something similar, and I suggest we will introduce something like a scalar product of two different functions, and from scalar product we will define the distance or magnitude of whatever of the function. So what can be a scalar product of two different functions? If you have f and g, we can always have integral dx. Now, obviously, this is something which corresponds to all the definition of a scalar product. First of all, it's a real number. It's linear by this argument and linear by that argument. It's commutative. It's associative, obviously. So everything corresponds. So this definition of a scalar product can be introduced into our set of functions. And since it completely corresponds to, in all the properties to scalar product of vectors, we can similarly define something like this to be a magnitude, well, this is square. I don't want to put square root, so I'll just put square here, of the magnitude of a function f. It's actually called norm instead of magnitude. Norm for a function is equivalent term for a magnitude of a vector. And if we have this, we can always have a distance between f and g defined as f minus g norm, which means f minus g times f minus g integral from a to b and square root. So we have defined the distance. Since we define the distance, we can define small neighborhood. Small neighborhood of function f0 is all g such that norm f0 minus g less than some kind of epsilon. So this is an epsilon neighborhood of function f, defined through the distance according to the definition of norm, and norm is defined in terms of scalar product. And scalar product is defined as integral. Or it can be some other definition of norm. Norm can be not related to scalar product. For example, norm can be defined just as maximum of f of x on AB. It's also norm. And the the distance between two different functions can be, again, maximum of f of x minus g of x on AB. This is also a distance, kind of a definition of distance. It means one function is not far from another. So if one function is this one, another should be somewhere around it. So the difference between them for any x does not exceed epsilon. So this is also a norm, or a distance, if you wish, between functions, and you can define minimum of a functional which it achieves at point f0, such that for all functions according to some definition of norm which are close to f0 along and a norm of deviation of function g from function f0, if this norm is less than epsilon. Whatever the definition of norm is, as a scalar product maybe, or as a maximum, or even another definition of norm, which is also very important in physics. Now, this is definition of the ordinates. So ordinates are not supposed to be differ by much. But what if you have a very sharp teeth here? So it can be very, very close, but with a very sharp teeth. Sharp teeth means derivative. In physics, derivative is a speed, right? So the speed of changing can be very, very high. And sometimes we don't want that. Sometimes we want to consider functions to be close to each other, if not only they're close by ordinates, but also close in first derivative, which means that in this particular case, the norm should be defined a little bit more strictly. It should be restricted not only by change of ordinates, but also change of first derivative. So it should be maximum between f of x minus g of x and maximum from f derivative minus g derivative of x, and maximum of these two, maximums. So that means that if I would like to talk about, if this is a norm between f minus g, if I will talk about a small neighborhood of function f, are all g which correspond to this, which means maximum of difference of ordinates and maximum of difference in first derivative does not exceed certain small number. So this is basically one definition of let's say minimum of functional f. I would like actually to introduce another one which is very close to directional derivative in functions of n arguments, which I was just explaining, and it seems simpler. Okay, so what do they mean? Again, very, very simple thing. Let's define, okay, now our f0 of x is assuming a minimum. What does it mean? Well, let's take some function, call it e of x, some function, which defines a direction in the same way as we were using a unit vector in n-dimensional space, which defines direction towards which we are measuring. And now let's consider function this one plus this times this, and check what is the value of the function. If this is greater or equal than f of f0 of x for t greater than 0 and less than tau, and tau should be some kind of a positive number, So if exists some kind of a number tau that this thing would be, so the deviation would be greater than the value at point f0 for any function e, we should really find this particular boundary. So in any direction, wherever I move, there is always some kind of a nearness which is defined by some kind of a real number, such that if I do not exceed this boundary, if t is still less than this tau, then my values would increase in any direction from function f0 to any defined e of x. Okay, so why is it better? Because for any particular e of x, if we choose it, we can differentiate it, because this is just a function of t. We can differentiate it and find basically some kind of equation which function f0 is supposed to satisfy. The problem obviously is that there are infinite number of these directional functions, so it's infinite number of directions. In case of n-dimensional space, we were saying that that's enough actually to have only n directions along each coordinate axis. In this case, it's not so simple. However, there are certain things which we can talk about, and that will be the subject of the next lecture. But meanwhile, my purpose today was to define, using this type of directional definition of minimum, to be able to enable in the future analyze the functional as a function of single argument t. Well, obviously this is the definition of the minimum. If you want maximum, that would be obviously the different sign. So in this case, the value of this should be greater than any value in the neighborhood, in which case it would be a maximum. So again, the definition is for any function e of x, nice function which is belong to the domain of the functional f. We have to find, there is an exist tau, there is some kind of a maximum deviation along this function x, such that this particular inequality is true for all t of this particular range. That's it for today. So I suggest you to read the notes for this lecture. You can find them on unizor.com. You go to Physics Plus for all course, and in this Physics Plus course there is a part called Lagrangian, and this is the second, I believe, lecture in that part. Now on the website I put not only the lecture, as I was basically, which you can watch, not only the video, but also the description, the notes, which I suggest you to read. Plus, it's very important to have the whole course basically in front of your eyes, because you can always return back and read something or watch some other lecture. So I suggest you to do everything through unizor.com. It's a totally free site. There is no advertisement, no sign-in required, unless you're studying under somebody's supervision. So basically that's just the knowledge for anybody to take, and I suggest you to take. All right, that's it for today. Thank you very much, and good luck.